All right, so today we're talking about particle kinetics, notably the force and acceleration method. Kinetics deals with how forces and motion interact with each other. So kinetics is the interaction of forces and motion. So everything you learned in chapter 1, which was kinematics and how geometry of motion is important, directly plays into this chapter as well, which is kinetics. So it's important to start off by looking at Newton's laws of motion. Law number 1 of Newton says that a body at rest or at constant velocity retains that state unless acted upon by a force. So if a body, I'm just going to call it a mass at rest, it's going to retain that state, so it wants to stay at rest or at constant velocity unless a force is acted upon. Law number 2 of Newton says that force is equal to mass times acceleration. This is a little bit confusing because the force here is not just the force that mass times acceleration is producing. It's not what we commonly call inertia. It's rather the sum of all the forces acting on a mass equal its mass times acceleration. So it's better to think about it that way. So if I have a mass that looks like this, and if I have all these little forces that are acting on it, I'm just going to use F here, sort of resembling the resultant of all these forces. Then what I get is F is equal to ma. And of course, this mass could be accelerating in some direction as well. This is really the notion behind law number 2. For law 3, I feel like it's the most commonly known. It's that for every action, there is an equal and opposite reaction. So if I'm looking at a mass again, and I have forces F1 and F2 being applied on this mass, they tend to be of equal magnitude and of opposite direction. So we can write this down as well. For every action, there is an equal and opposite reaction. Okay, so the next step is to put all these 3 laws together, and this is where we get the concept of the equation of motion. So we have the equation of motion. Equation of motion really stems from Newton's second law, and it says that the sum of all the forces that a mass experiences equal its mass times acceleration. So if I have a mass and I have all these individual forces, and you could have a lot of these individual forces, ultimately the resultant of these is equal to its mass. So this is the particle mass and its acceleration. So we can already see that there is a direct relationship between forces and motion of a particle. And of course, in 3-dimensional coordinates, we could say there is a decoupling between the x, y, and z axes. So all the forces, so all the forces in the x direction multiplied by the I unit vector. I is the unit vector in the x direction, plus all the forces in the y direction, plus the j unit vector, meaning multiplied by the j unit vector, plus sigma fz k. K is the z unit vector. All of this is equal to mass in the corresponding acceleration direction. So we have ax, I, ay, j, plus az, k. So in 3D coordinates, which is what we have here, we're assuming that we could do we can analyze Newton's forces, Newton's laws, by decoupling each of the axes. So if you're interested in the x direction, you only work in the x direction. You only deal with the I unit vector. You don't have to really combine them all together. So that's really a benefit of this method. It allows this decoupling. So now we can look at an example. This is kind of a simple example, but it really illustrates some really fundamental concepts. So we are given a crate that is of mass 300 units. I guess this is not the mass, right? This is the weight, so it's 300 units. It's sliding on a surface. This is kind of the ground that the crate is sitting on. It's sitting there. There is a force being applied of magnitude 200 newtons. The angle that the force makes with the horizontal axis is 30 degrees. And you're being told that the block is at rest to begin with. So this is the beginning condition. And suddenly it's subject to 200 Newton force. And what you really have to find is the following two items. You have to find the velocity when t is equal to 5 seconds. And you have to find the position of the mass when t is equal to 5 seconds as well. So that's really what we need to do. The last thing, I guess, that I've missed here is that there is a coefficient of friction is 0.2. This is the coefficient of friction. We call it mu, and we use it for our analysis. Okay, so whenever we have a dynamical problem, I always start off with a free body diagram. So this is my free body diagram. It's really helpful to always draw this because it prevents you from missing some fundamental component of the force. Okay, so this is our mass again. And what we have to do now is to plot all the forces that we have over this mass. So obviously we have gravity being applied. So W is the self-weight of the mass. So W is 300 newtons. That's given to us. If there is a vertical force being applied, obviously there has to be a normal force resisting it. So that's N. If the mass is going to slide in the right direction, right, it's going to be because there is a force here. So it's P is equal to 200 newtons. So this force is going to be there. So if we're sliding right, we can also say there's a friction force going in the left side. Your friction force is always in the opposite direction of your motion. So my 200 Newton force that's applied, it's going to make my mass slide to the right. Thus, the friction has to be going left. That's important to know. And lastly, I guess before the last thing, let me do a 30-degree angle here. Okay, oops, excuse me. So there's a 30-degree angle there. And the final thing to note here is the mass times acceleration. So remember how Newton's three laws stated, or I guess Newton's first law, it stated that masses would like to retain their existing states unless acted upon by force. Well, that's what we need to be looking at. If my mass is going to be pushed to the right and my mass wants to stay where it originally was, then there is going to be acceleration experienced going left. So there's a mass times acceleration going to the left. So my mass is getting pushed to the right. It wants to stay where it was. So the mass times acceleration is facing the left direction. So that's also important to note. Okay, so in general, always keep this in mind. It's whichever way the force is being applied, whichever way the mass starts moving, the acceleration experienced by the inertial component is in the opposite direction. I guess the other thing that's important is mass here is 300 newtons divided by 9.81 meters per second squared. So we'll use that in a few seconds. Okay, so we have our free body diagram. Now we want to sum up all the forces. So this is the sum of forces. We said that we would like to decouple the x and y directions. That's a benefit that this method offers. So what we could say is we have all the forces in the y direction have to equal to 0. So if I look at my forces in the y direction, and by the way, here I always like to provide a directionality to like where the positive force is. So if the resultant forces are positive, then they're going up. So in this example, I chose up to be positive. So with that in mind, I'm going to sum all the forces. N is going to be facing upwards. W is facing downwards. So that's 300 newtons. And we have the vertical component of the external force, which is P. So we have minus, it's in the downwards direction, right? So we have minus P sine 30. And P here is 200 newtons. Right? And this whole thing is equal to 0. There is no mass times acceleration in the vertical direction. So this whole thing is equal to 0. If we do our algebra correctly, we have N is equal to 400 newtons. Okay, so that's useful. We had to calculate N because we want to know what the friction force is. And friction force is always a component of the normal force. Okay, so now we can say friction force is equal to mu N. That's really a fundamental equation in physics. We always do mu times N, and this is equal to 0.2. That's what the question stated as our friction coefficient times the 400 newtons. And we have a resultant of 80 newtons. Okay, so we've done all the vertical analysis that we needed to do. Now we could do horizontal analysis. So again, sigma fx is equal to 0. We choose a direction that's positive. In this case, I chose right to be positive. I have my external force, P cosine 30. I have my friction force in the opposite direction. Let's look at the free body diagram. So 200 is going to the right. Friction force is going to the left. Mass times acceleration is sort of resisting the direction of motion, so it's going to the left as well. So this is MA. And so this whole thing is equal to 0. I already know that FF is 80. I know M is, I guess it's around 30, right? So it's 300 divided by 9.81. And the only thing that I don't know is the A. And P we also know as well. This is 200. So here is what we do next. We isolate A on the left side, moving everything else to the right. So we have A is equal to 1 over m P cosine 30 minus that. Now just plugging all the parameters in, we have 9.81 over 300. That's the inverse of the mass. 200 cosine 30 minus 80. And this whole thing is equal to 3.048 meters per second squared. So from the moment where the force is applied on the mass begins to accelerate. That's really what's happening. It's sort of an instantaneous force that's applied. So at that very moment, it's when the mass starts accelerating. So if I were to do a plot of the, so if I did something like this, and I was interested in my acceleration time plot, I could say that acceleration is constant from the onset when the force is applied. So this is 3.048 meters per second squared. So that's important. All right, so now we have to utilize kinematics that we used in lecture 1, right? So we are given a constant acceleration, and we want to go from the constant acceleration into velocity into displacement. Now, of course, you could do this. Using integration. So you can have velocity is v is equal to integral of the constant acceleration dt, in which case you would get 3.048 t plus the constant of integration, right? You can also do a second integral. So we have displacement now. So we have, in this case, we have x. X is what I call displacement, is equal to the second integral for v dt. And this is just integrate the v again. So we have 1.524 t squared plus the first constant of integration times t plus c2. And those constants of integration are going to disappear because if we have the at rest condition to begin with, at rest, so this means that x naught was 0. So x at time 0 was 0, and v at time 0 was also 0. So with this second relationship, I can plug it into my velocity equation, and I have v0 is equal to 0, and so I have 3.048 0 plus c1. This whole thing is 0, therefore c1 must be 0 as well. I can do the same thing for x, and I will get c1 and c2 are both equal to 0. So this tells us that c2 is equal to 0. Okay. So we've established these two relationships. This is really the first part of the relationship that we care about, this velocity relation, and we have the x. And this first part is also what we care about, because all those constants ended up being zeros, right? Okay, so let's grab these two equations, go to the next page. And the time we were interested in was t is equal to 5 seconds. So the answer is as follows. We have x5 is equal to 1.524 5 squared. This gives us 38.1 meters. So 5 seconds after the force has been applied, we've moved 38 meters. And in that time period, we achieve a velocity of 15.24 meters per second, right? So that's it. These are the two answers we were looking for. And that concludes a very simple example with the force and acceleration method. Now we want to look at another example that's a little bit more sophisticated, right? We always want to slowly add sophistication and learn the concepts that way. That's a more realistic approach at learning hard concepts. All right, so here we have, we're given a slope that looks like this. On this slope, I have two masses. So we have mass A, so that's mass A, and I have mass B on the slope as well. It's kind of smaller. There is a rigid link that is connecting the two. It looks like this. You kind of think of this link as being completely rigid, having no mass of its own, and it's only there to connect the two together. So if there's any forces, it's going to pass them between the two masses. So we have the two masses. The only other thing we have to know is the slope of this surface. This is 30 degrees. MA here is equal to 10 kilograms. MB here is 6 kilograms. By the way, note that in this example, we're dealing with mass. In the last example, we dealt with weight. So that's the only difference. Okay, so we also want to know the coefficients of friction. If you assume that A and B are two different materials, well, the way they interact with the substrate, the material underneath them, the surface underneath them, is going to be different as well. So you have two different coefficients. So here we have mu A is equal to 0.1. We have mu B is equal to 0.3. Okay, so you're giving all the coefficients of friction, and what we want to do is we want to place these masses on the surface, and we want to see what the level of force in the link is. I guess this is what the question is asking. So what is the force that's going to be in the link, and what is going to be the acceleration that the two masses experience together? So, the acceleration, we don't really know which way it's going to go, right? The acceleration. I guess I have a feeling as to which way it's going to go, but we'll talk about that. All right, so we have two different masses. We first want to do a free body diagram. It's best to break them up and to analyze them separately. So here is the first mass. This is the free body diagram, by the way, FBD. This is the first mass. So, we can always deal with the classic stuff. It's the weight. We have 10 kilograms times 9.81. So that's W. W is applied at an angle of 30 degrees. So that's important. The surface that it's sitting on, that the mass is sitting on, is going to impose a normal force, right? Normal at A. If we have a slope downwards, it's safe to say that the two masses are going to slide in that direction, right? So if mass A is going to be going in the downwards direction, so like in this direction, the friction force that it's going to experience is in the opposite direction. Remember, friction is always in the direction of, in the opposite direction of motion. So we have F of F is equal to 0.1 NA. And this is where we got the friction coefficient. Another thing we have to consider is that If the mass is going to be sliding downwards, but it wants to stay in the same place, then the inertial component is going to be in the upwards direction. So let me choose a different color and note that down. So if it's sliding downwards, then MA is in the upwards direction. So with this free body diagram, oh, one more thing. There's also the force that the rod is imposing, this rigid link. I don't know which way it's going to face. Let's just say this is the force. Forces are a little bit more complicated, so we don't really know which way they're going to face. Okay. So let's do the sum of forces in different directions. Let's choose the black color. We have sum of forces normal to the surface. So we can do sigma Fy is equal to 0. So what do we have? We have Na, it's a semicolon. When we have Na, we have 10, 9.81. That's the W. That's the weight. You have to align it with this angle here. So cosine 30. So you're aligning the weight with the normal to the surface. And this whole thing is equal to 0, right? There's really no acceleration normal to the plane of the surface because the mass is just sitting there. It's at equilibrium. Okay, so we have this going, and then all we have to do is to calculate NA, and just move everything to the right-hand side, and you should have 84.96 newtons. All right. So once we know this, then we can move to the tangential direction to the slope. And for this example, we could say, going down is perhaps positive. Let me scroll down more. So this is positive. Sigma Fx is equal to 0. Okay, so for this, I guess I want to start by looking at the weight of the mass. We have 10, 9.81. This time, it's the horizontal component, right? It's this component. So we are looking at sine 30. So this is going downwards, it's positive because that's what we chose. Friction force is going upwards. We have minus 0.1 NA. We also have the force that's imposed by the link. I chose upwards to be the direction, so it's minus F. So we have this. And lastly, we have minus MA, the inertial force, Newton's second law. And this whole thing is equal to 0, right? We already know what MA is, that's 10. We know what NA is, that's right here, it's 84.96. The two unknowns we have are F and A. So we have, let's clean this up just a little bit. We have 40.55 minus F minus 10A is equal to 0. All right, so we ended up with this relationship. It's one equation, two unknowns. So as you can tell, we are going to have to develop another equation with two unknowns. Then we have two equations, two unknowns, and we can solve this. All right, scroll down more. Now we look at the second mass. Second mass is also at a slope. We have this. The force is going to be acting in equal and opposite directions, right? We're always using Newton's laws. We have the weight, which is 9.81. So we have this. We have the 30-degree angle, the normal force. We call this NB. If it's sliding downwards, friction will be in this direction. So F of friction is equal to, the coefficient was 0.3 in this example. NB, so that's what we have. And what's left is the inertial component. Again, if it's sliding downwards, it wants to stay in the same place. So the inertial component is as follows. We have MBA. And by the way, the reason why I'm using a constant acceleration for both masses is because they're linked together, so they're accelerating with the same rate of acceleration. So the two A's are the same. All right. So let's do sum of forces again. We have sum of forces in this direction, which is normal to the surface. This is Fy is equal to 0, semicolon. So what I have is NB minus 9.81. That's the W, looking at its vertical direction, cosine. I meant vertical to the surface, right? So cosine 30 is equal to 0. So this is nice and simple. NB is equal to 50.97 newtons. That's an N. All right. Now we have to do the analysis in the tangential direction, which is this way. I choose down to be positive. Sigma Fx is equal to 0. So what we have is F is going downwards. We have plus 9.81, the W sine 30. We have minus 0.3 NB. What was NB? It was 50.97. That's the friction force. And we have the acceleration, right? It's basically what's MB times A? It's 6 times A. And this whole thing is equal to 0. And so putting it all together and simplifying, we have F plus 14.14 minus 6A is equal to 0. All right, perfect. Two equations, two unknowns. I don't have to go into the details as to how to solve this. You guys are better at maths than me. If we do it together, we get A is equal to 3.42 meters per second squared, and we get F is equal to 6.37 newtons. By the way, if your force ever ends up being negative, it means that the direction of the arrows, direction of the force vector that you chose was incorrect, and that you just have to flip it, or you just, you state that the force is in the opposite direction of that. Alrighty, well, I hope you guys found this lecture to be useful, and I'll see you next time.